Hello, my name is Thomas Rodriguez, and I will be going over Lab 3 for Physics 2212. So the purpose of this lab is to create circuits, specifically two circuits, one that just involves two resistors, and then the other that resolves a resistor and a capacitor, and to make predictions on how resistors being in parallel or series change the voltage or current of a circuit. And then we would measure the current or voltage using a multimeter. For the fundamental physics principles, first is Ohm's law, which is that voltage is equal to current times resistance, meaning that the voltage is proportional to the current of the circuit and its resistance. Then there's the node rule, which is that the current going into the circuit is equal to the current going out of the circuit, so no current is lost. And then there's the loop rule, which is that the sum of all voltages in a circuit would be equal to 0. For this experiment, the model we'll be using is a circuit diagram. For the system, it is the circuit itself with its internal electric forces and electric fields, and in the surroundings it would be any external force affecting the circuit. For the main results of the experiment, the loop rule and node rule were proven true. As for the details of specifically the series circuit experiment, we have a multimeter here, which was used to calculate the current and the voltage. Then we have the battery, which consisted of two 1.5 volt batteries. And then also there was a resistor that would be paired together along with these alligator clips. So for the initial conditions, we were given two 1.5 volt batteries, two resistors, one that's 47 ohms and the other that's 100 ohms, and two ammeters. What was observed in the experiment was that the current at location I1, which is over here, and I2, which is over here, they are both 20 milliamps. This was calculated by doing that current equals voltage divided by resistance, and since the total voltage is 3 volts, and the total resistance, which is the sum of both the resistors, is 147 ohms, this would give us 20 milliamps. And then this also proves the node rule, which is that the sum of the current in is equal to the sum of the current out. And then the reverse of these two currents is negative 20 milliamps. The voltage of the battery that we measured was 3.07 volts, and we've also measured the individual voltage of the 47 ohms and the 100 ohm resistor. So for the full 47 ohm resistor, it was 0.99 volts, and for the 100 ohm resistor, it was 2.08 volts. So to prove the loop rule, using the observed voltages that we had, we could see that when doing that the delta V, or delta voltage, is equal to 0, we were able to calculate that it indeed matches up, that the observed voltage at the battery is equal to the total sum of these voltages, or in other words, the voltage of the battery minus the voltage of each resistor would be equal to 0. And then here's the graph of the electric potential versus the location across the current. So after going through the first resistor and after going through the second resistor, the voltage would equal 0. Or sorry, the voltage or electrical potential. As for the RC circuit experiment, we would have a capacitor, and then we would have a light bulb to the right of it. So the light bulb would turn on when going through the capacitor when it was fully charged, but then the brightness would diminish rapidly afterwards. So when we put a 10 ohm light bulb, it would take around 12 seconds to discharge for the capacitor to discharge, and when it was a 20 ohm light bulb, it would take around 22 seconds for the capacitor to discharge. In conclusion, the resistance of the wires, some assumptions we made is that the resistance of the wires would be negligible, so as not to interfere with the calculation of the current, and also that no external electromagnetic forces would affect the circuit. Some possible errors was stopping the stopwatch at the wrong time for the RC circuit when we calculated these times, and also the misreading of measurements on the multimeter for the series circuit experiment. For the what if question, what if you charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? So if there was no resistor in the circuit, then the capacitor would ideally reach full charge instantly. However, because the wires do have a small amount of resistance, this prediction would not happen perfectly in real life. That concludes this lab, and thank you for listening.